Today, at 13:19 UTC, the Sun detonated. Officially, on the record, one of the most violent eruptions of 2026, a plasma cloud the size of nothing, your brain is equipped to visualize, launched at 650 kilometers per second. Official monitors use the word extremely violent. Independent observers said colossal, and you felt zero of it. No storm, no aurora, KP sitting at a sleepy 2 like absolutely nothing happened. Here's the part that should bother you. It wasn't weak, it wasn't a false alarm. Every instrument confirmed it was exactly as serious as it sounds. The only reason your day was fine is that it was aimed somewhere else. That's it. One geometric accident standing between today's non-event and a completely different headline. And the sunspot that fired this off, the one that's been erupting since before it was even visible to Earth, is still active, still rotating, directly toward us. 4 to 6 days. Same region, same energy. No more geometry to save us. Stay around because the mist just became a countdown. If this has you unsettled, hit like and subscribe to the Sky Lab because we are just getting started. The region is still active, the countdown is running, and we'll be here tracking that in real time. You want to be here for what comes next. Now, let's get into it. Part 1. The event that should have been a storm. At 13:19 UTC on May 10th, 2026, the Sun did something that should have ruined your day. Not in a minor check your phone kind of way. Not in a the northern lights were visible a bit further south than usual kind of way. We're talking about the kind of event that space weather forecasters mark in red. The kind that gets shared between monitoring stations with language that professionals almost never use in official communications. Words like extremely violent, words like colossal. These are not the words scientists reach for when they are trying to stay calm. These are the words that slip out when calm stops being an option. So let us talk about what actually happened, because the numbers alone do not tell the full story. An M5.7 solar flare erupted from a sunspot region on the eastern limb of the Sun. Now, if you are not fluent in solar classification, here is a quick way to frame it. Solar flares are rated by letters A, B, C, M, and X, each one representing a tenfold increase in X-ray output over the last. M-class flares sit in the 4th tier, and an M5.7 puts you more than halfway toward the X-class threshold. It is not quite the top of the scale, but it is not the bottom either. Think of it like a Category 3 hurricane being described as not a Category 5. Technically accurate, not exactly reassuring. But the flare itself was only part of the story, and honestly not even the most alarming part. Paired with that X-ray burst was a coronal mass ejection, a CME, travelling at approximately 650 kilometers per second. For context, that is about 1.45 million miles per hour. A plasma cloud the size of something you genuinely cannot fit inside your imagination, launched off the surface of a star and sent screaming outward through the solar system at a speed that makes the fastest spacecraft humanity has ever built look like a paper boat on a still pond. The Space Weather Prediction Center, which is the United States agency responsible for monitoring these events, issued an R2 radio blackout classification, moderate level, affecting the sunlit hemisphere of Earth. High-frequency radio communications, the kind used by aviation, emergency services and maritime navigation, experienced disruptions on the side of the planet facing the Sun at the time of the flare. And then something strange happened. Nothing else did. No geomagnetic storm, no expansion of the auroral oval pushing colourful lights down toward the mid-latitudes, no reports of satellite drag anomalies, no grid disturbances, no alerts from operators of sensitive infrastructure. The planetary K-index, which is the global measure of geomagnetic disturbance, rated 0 to 9, barely climbed above 2. 2, on a scale where storm conditions begin at 5, and where the May 2024 event that made headlines around the world peaked above 8, a KP of 2 is the planetary equivalent of a light breeze. You could sit outside with a cup of tea and not notice a KP2. It is, in geomagnetic terms, a perfectly ordinary Saturday. Here is why that should feel wrong to you. Events of this magnitude, an M-class flare in the upper half of that range, paired with a fast coronal mass ejection, do not typically produce KP2 conditions. They produce measurable geospace responses. They bend the magnetosphere. They energize the outer radiation belts. They show up in the data in ways that operators and forecasters have come to expect. And yet, by every instrument watching Earth's magnetic environment, the planet registered almost nothing. Now, before anyone jumps to the obvious conclusion that the instruments were wrong or that the event was somehow exaggerated, let us be absolutely clear about what the detection record showed. Multiple independent systems confirmed this as a genuine high-energy event. X-ray flux sensors aboard the Gauss satellite constellation recorded the spike with precision. Type 2 radio bursts, which indicate a CME-driven shockwave propagating outward through the corona, were detected. The 10-centimeter radio flux, a standard proxy measurement used by forecasters to gauge solar activity, spiked from a background level of approximately 122 solar flux units to a peak near 550 solar flux units. That is not noise. That is not a calibration error. 550 solar flux units represents a massive surge in electron acceleration in the upper solar atmosphere, and it lined up almost perfectly with the timing of the flare peak. Multiple instruments, multiple signal types, multiple confirmation layers. This event was real, it was strong, and it was exactly what it looked like. So why did Earth feel nothing? That answer comes down to one of the most counterintuitive ideas in all of space weather. The idea that a massive violent event on the Sun can be completely invisible from Earth, not because it was weak, but because it was aimed somewhere else entirely. We live in a solar system where 93 million miles is actually a very small slice of the sphere of influence surrounding our star. The Sun does not erupt toward us specifically, it erupts outward, in all directions, following the magnetic geometry of whatever active region happens to be releasing energy at that moment. And on May 10th, 2026, at 1319 UTC, the geometry was not pointed at us. This was not a near miss. This was not a case where Earth narrowly avoided catastrophe by some margin of luck or stellar fortune. Earth was not in the path at all. Saying we survived this event would be like saying you survived a car accident that happened on a different street. You were never in any danger, not because the accident was minor, but because it literally did not happen where you were standing. And here is what should keep you watching. The region that produced this event is not staying where it is. The Sun rotates, slowly but with absolute inevitability, turning its active regions toward us on a schedule you can calculate to within a day. The sunspot region responsible for May 10th's eruption was sitting at approximately east 65 degrees heliographic longitude at the time of the event, well out on the eastern limb, comfortably outside any trajectory that would send plasma toward Earth. But that is a temporary condition. In 4 to 6 days, that same region will have rotated directly into Earth-facing position. The geometry that protected us today will have been replaced by the geometry that maximizes impact. And the region, as we are going to spend a lot of time discussing, has already shown us exactly what it is capable of. This video is not really about what happened today. Today was a preview. Today was the trailer. What we are actually talking about is what happens when the main feature starts, and that window opens in a matter of days. But first, let us talk about why you almost certainly did not hear about any of this, because there is a concept in space weather that I want to introduce right now, and it is going to reframe the rest of everything we discuss. The concept is sometimes called space weather invisibility. It refers to the fact that major, even catastrophic solar events can unfold without registering a single alert on your phone, without making a single headline, without producing a single visible aurora, because the planet they would have affected was simply not in the crossfire. The Sun could be undergoing some of the most energetic activity of the current solar cycle right now, and if none of it is pointed at Earth, your Tuesday proceeds completely undisturbed. You go to work, you drink your coffee, you complain about traffic, completely unaware that the star powering your entire civilization is doing something extraordinary in a direction you will never see. That invisibility is not comforting. That invisibility is exactly the condition that catches people off guard. Because the events that do not hit us are not teaching us anything. They are not adjusting our threat level. They are not recalibrating our forecasts or updating our emergency plans. They pass unnoticed, and we carry on assuming the baseline is normal, right up until the moment the geometry shifts and the baseline stops being normal very quickly. On May 10th, 2026, something extremely violent erupted from the Sun. The only reason you're reading about it rather than experiencing it is a matter of degrees, specifically about 65 of them. In a few days, that number will be 0. And I think you should probably know what that means. Part 2. The geometry that saved Earth. Let us do some astronomy together, because the geometry here is actually the most important part of the entire story, and it is not complicated once you have the right mental picture. Imagine the sun at the centre of a clock face, and imagine Earth sitting somewhere along the outer edge. Now, the sun has its own coordinate system, heliographic coordinates, that works roughly like longitude on Earth. 0 degrees is the central meridian, the point on the sun's disk that faces Earth most directly. Positive numbers to the east, negative or west numbers to the west, going out to 90 degrees in either direction before you reach the limb, the edge of the visible solar disk as seen from our position. On May 10th, active region 4436 was sitting at approximately north 21, east 65. The north 21 just tells us how far above the solar equator the region sits. The east 65 is the critical number. East 65 means this sunspot was sitting 65 degrees away from the point on the sun that faces Earth directly. It was out on the far eastern portion of the visible disk, close to the limb but just barely in view. If you had access to solar imaging equipment, you could see it at the edge of the sun's face like something just peeking over the horizon. Now why does that matter? Because a coronal mass ejection is not like a laser. It does not fire in a single precise line from one specific point. It expands outward in a cone shape, centered on the axis of the erupting magnetic field region, but spreading outward in all directions around that axis. Think of it like the beam of a flashlight. The center is bright and concentrated, and the edges fade out, but the whole thing covers a cone-shaped volume. The CME from active region 4436 had an estimated speed of 650 km per second and a fairly typical angular width. But the central axis of that cone was pointed roughly 65 degrees away from Earth, out toward the eastern region of the inner solar system, away from our orbital position entirely. For a CME to produce a significant geomagnetic storm, it typically needs to be aimed within what forecasters call the geoeffective longitude window. That is roughly east 30 to west 30, the 60-degree band centered on the point facing Earth directly. Outside that window, CMEs can still produce glancing blows, particularly if they are unusually wide or fast enough that the outer edges of their expansion cone clip Earth's magnetosphere. But a well-centered eruption at East 65 is in most cases outside that window entirely. The plasma cloud expands into interplanetary space in a direction that simply does not intersect Earth's orbit in any meaningful way. The event on May 10th was exactly that. The CME did not graze us. The outer edges of the expansion cone did not clip our magnetosphere in any way that registered. The SOHO and STEREO spacecraft, solar imaging missions that watch the sun from different angles and give us three-dimensional perspective on CME propagation, confirmed the lateral trajectory. What looked from Earth like a violent eruption on the edge of the sun was, from a perspective slightly outside our orbital plane, a plasma cloud heading almost perpendicular to our position. Earth was standing beside the highway. The car passed at high speed, but it stayed in the lane. Here is what I want you to understand about that analogy, though. The difference between standing beside the highway and standing in the lane is not always as large as it seems. In solar terms, the difference between a miss and a direct hit can be as small as 20 to 30 degrees of heliographic longitude. A shift of about 25 degrees in the location of that eruption, which in terms of physical solar surface corresponds to a distance that sounds large, but represents a tiny fraction of the total solar disk. And we are having a very different conversation today. 25 degrees is the margin. 25 degrees separates nothing happened from geomagnetic storm response teams are mobilizing. That is not a comfortable margin. That is not the kind of margin that lets you relax. The thing that most people do not think about when they consider solar flares is that the sun does not flare with any awareness of our position. There is no version of this where a sunspot region sends out scouts first, checks the geometry, and then decides when to release. The energy builds, the magnetic field becomes unstable, and it releases when physics demands that it release, regardless of where Earth happens to be at that moment. We are passengers on a planet that has no say in when or where these things happen. All we get to influence is how prepared we are when the geometry lines up against us. and the geometry that protected us on May 10th is changing right now at about 13 to 14 degrees per day, as the Sun's rotation carries active region 4436 steadily toward the centre of its disk, toward the point where it faces Earth directly, toward the geo-effective window that will make the next eruption, if there is one, something Earth cannot simply ignore. Now, a reasonable question at this point is, how certain are we about that trajectory? How precisely can we track where an active region is and where it is going? The answer is quite precisely. Solar rotation is not a chaotic or unpredictable process. The Sun rotates differentially, meaning different latitudes rotate at slightly different speeds. But for a region at about 21 degrees north latitude, the rotation period is close to 27 days, giving a daily longitudinal movement of roughly 13 to 14 degrees. Active region 4436 is at east 65 today. Each day it moves west by about 13 degrees. At that rate it enters the outer edge of the geo-effective window, east 30, in approximately 2.5 days. It reaches central meridian passage, the most Earth-facing geometry possible, in roughly 4 to 5 days. The timeline is not a guess, it is arithmetic, and the arithmetic says that the protection afforded by geometry on May 10th has an expiration date measured in days. So the only real question is whether active region 4436 will still be active when it arrives. Whether the energy that produced an M5.7 flare while the region was barely visible around the limb of the Sun will still be there, still building or still releasing, when the geometry shifts to maximum exposure. And to understand why that question is genuinely alarming, you need to understand what kind of region this is, because it is not behaving the way a region this size and this magnetic complexity is supposed to behave, and that is worth spending some real time on. Part 3. The multi-signal confirmation of a real event. Before we get into the region itself, let us close the loop on something, because I can already anticipate the skeptical viewer asking a fair question. How do we know this event was as strong as described? How do we know the alarm among monitoring communities is justified rather than overstated? The answer is that this event left fingerprints on every instrument that was watching, and those fingerprints told a consistent story. The X-ray classification of M5.7 is the starting point, but it is also the least interesting piece of the confirmation. X-ray flux measurements from the GUS satellites are incredibly reliable, but a flare classification alone does not tell you whether a CME was produced. Some M-class flares, a significant fraction of them actually, are what are called confined flares. The magnetic energy releases, the X-ray spike happens, but the overlying magnetic field prevents any plasma from actually escaping the Sun. No CME, no particle stream, no geomagnetic consequences even if the Earth were perfectly aligned. The energy dissipates locally and the Sun moves on. If May 10th's event had been a confined flare, this video would not exist, but it was not confined, and we know that because of what the radio detectors picked up. Type 2 radio bursts are one of the most reliable indicators in solar physics that a CME-driven shockwave is propagating outward through the corona. When a fast CME pushes through the solar atmosphere, it drives a shock front ahead of it, a pressure wave moving faster than the local Alphen speed, which is the characteristic speed of magnetic waves in that environment. That shock accelerates electrons, and those electrons emit radio waves at frequencies that decrease over time as the shock moves outward into progressively less dense layers of the corona. On a spectrograph, this shows up as a characteristic downward drift in frequency, a signal that sweeps from higher to lower radio frequencies over the course of minutes. That frequency drift is not a coincidence, it is a direct physical signature of an outward propagating shock wave, and on May 10th, that signature was there. The frequency drift rate from the Type 2 burst was consistent with a shock propagating at approximately 600 to 650 kilometers per second, which lines up almost exactly with the CME velocity estimated from coronagraph imagery. These are two completely independent measurement methods converging on the same number. That is not a coincidence either. That is confirmation. Then there is the 10 centimeter radio flux. The background level on May 10th was sitting around 122 solar flux units, already slightly elevated above the long-term average baseline, reflecting the general activity level of the current solar cycle. At the time of the flare, that reading spiked to approximately 550 solar flux units. Now, those numbers may not mean much in isolation, but here is the frame that makes them meaningful. A solar flux unit reading of 550 represents a surge of about 4 times the background level. For context, on a quiet day during solar minimum, the 10 cm flux might sit around 70 or 80 solar flux units. A reading of 550 is not an anomaly at the edge of the measuring range. It is a very large, very clear signal of intense electron acceleration in the upper solar atmosphere. It is the kind of number that makes the monitors put down their coffee. What all of this adds up to is what solar physicists sometimes call energetic completeness. The event had all 3 components: radiation in the form of X-ray flux, energetic particles in the form of accelerated electrons producing radio emission, and plasma in the form of the confirmed coronal mass ejection. All 3 signals appeared within minutes of each other, which suggests the underlying magnetic reconnection event was well organized and coherent, not a partial or fragmented release, but a clean, powerful discharge of stored magnetic energy across a well-defined magnetic structure. And here is the detail I want you to hold on to as we move forward. Events with this particular combination of signals, type 2 burst, significant 10 cm flux spike, confirmed CME, tend to be the ones that produce meaningful geomagnetic storms when they are Earth-directed. Not every fast CME produces a strong storm. Not every M-class flare produces a fast CME. But when you see this specific combination of indicators, the event has the characteristics of something that would have consequences if it were pointed at us. The signals do not tell us the trajectory, they tell us the strength, and what they confirmed on May 10th was that the strength was real. So the next question, the question that everything in this video is building toward, is not whether this was a strong event. It was. The question is what produced it. Because the region responsible is not supposed to be doing this, at least not according to the forecasts. Part 4. The region that shouldn't be doing this. Active region. 4436 is not a spectacular sunspot group on paper. When you look at the standard metrics, area coverage, magnetic complexity classification, spot count, it sits comfortably in the category of moderate, watch but do not panic. Its area is listed at approximately 150 millionths of a solar hemisphere. It has about 6 visible sunspots. Its magnetic classification sits in a moderate range. The kind of configuration that solar physicists look at and say, possible flare producer, monitor accordingly, not get the emergency coordination teams on standby. If you submitted these numbers to a solar physicist without context, they would file active region 4436 somewhere in the middle of the pile. They would not flag it as the most alarming thing on the solar disk, and yet here we are. The M5.7 flare on May 10th was not the first sign that this region was misbehaving relative to expectations. On May 7th, 3 days earlier, before active region 4436 had even fully rotated into view from behind the solar limb, the region produced an M2.6 flare. Let that sit for a moment. The region was behind the limb. From Earth's perspective, only the very top of its corona was peaking above the solar horizon. We could not even see the sunspot group itself, only the highest and most diffuse upper atmosphere above it. And from that position, from behind the edge of the sun, it was already producing M-class flares. This is not normal behavior for a moderate sunspot group. The term that solar physicists use for this kind of region is Born complex. It is a phrase that carries more weight than it might initially suggest. In most cases, a sunspot group goes through a gradual development process. Magnetic flux rises through the solar interior and breaks through the photosphere, the visible surface, in a relatively organized way. The spots emerge, they grow, they develop complexity over days as the magnetic polarities interact and the field lines tangle. There is a ramp-up period. There is a learning curve, so to speak, for the region's flare-producing capability. Born complex regions skip that process. They emerge from beneath the solar surface already carrying a pre-organized, highly tangled magnetic structure that was built up below the visible layer. The complexity does not develop over days. It arrives fully formed, like someone who shows up to the chess match already knowing all the advanced gambits. The energy availability is immediate. The potential for flares is there from the moment the region becomes visible, or in the case of active region 4436, even before it becomes visible. This matters enormously for the next few days, because one of the models forecasters use to estimate when a region might be winding down is the idea that large flares deplete stored energy. The region builds up a reservoir of magnetic stress, the flare releases some of that stress, and in the aftermath the region is temporarily less capable of another large event. In many cases this is true, but born complex regions that are continuously drawing on a deep pre-organized magnetic structure, do not necessarily follow that depletion model. They can sustain flare production across multiple events without showing the energy drawdown that forecasters would normally expect. There is also another possibility that makes forecasters uncomfortable, and that is continuous flux emergence. If the magnetic structure beneath the surface is still actively pushing new flux upward through the photosphere, the region is not just sitting on a fixed reservoir of stored energy, it is being continuously refilled. Every hour that passes, new magnetic stress is being added to the system, potentially replacing or even exceeding whatever was released in the last flare. A region in this state is not on a trajectory toward quiet, it is on a trajectory toward continued or escalating activity. And here is the detail that cuts right to the centre of the story. Between May 7th and May 10th, active region 4436 went from an M2.6 flare, still significant, still M-class, but toward the lower end, to an M5.7. That is a jump of roughly a factor of 4 in X-ray energy output in 72 hours. That is not a region winding down after a release. That is a region that produced a moderate event and then produced a stronger one days later. The trajectory in those 3 days was upward. Which brings us back to the geometry. The region that is escalating in flare intensity, that was born complex, that was already active before we could even see it. That region is now rotating toward us, day by day, degree by degree, at 13 to 14 degrees per day. And the only protection we had on May 10th, the 65 degrees of longitude that put the eruption cone aimed somewhere other than our home, is being eroded every single day. There is another sunspot region on the solar disk right now that is significantly larger and technically more complex than active region 4436. That region has been the subject of most of the official forecasting attention this week, but it has been relatively quiet, producing only modest C-class events, while the smaller, less impressive region has been doing the heavy lifting. We will come back to that contrast in detail later, because it tells us something important about the limits of solar forecasting. But for now, keep this in your mind. The region that is not supposed to be the problem is the region that produced today's event, and it is heading directly toward us. Part 5. The core tension. Let us talk about what the next 4 to 6 days actually look like, because this is the part of the story that matters most, and where the central tension of everything we have discussed comes into sharp focus. Solar rotation carries active region 4436 westward across the solar disk at approximately 13 to 14 degrees of heliographic longitude per day. On May 10th, as we established, the region sat at approximately east 65. That means on May 11th, tomorrow, it will be near east 52. On May 12th, near east 39. On May 13th, near east 26, which is inside the geo-effective window. On May 14th, near east 13, approaching central meridian. On May 15th or 16th, central meridian passage, directly Earth-facing geometry, maximum potential impact for any CME the region chooses to produce. Write that timeline down if you want. May 13th through May 16th is the window. Those are the dates when active region 4436 will be in the position where an eruption like May 10th's would not miss, where the plasma cloud would not spend its energy somewhere in the interplanetary void between here and Venus, where the 650 km per second CME we watched depart today would be aimed directly at the planet you are standing on. Now, here is the central question, the one that the entire rest of this video circles back to, the one that forecasters are actually losing sleep over right now. Will the region still be active when it gets there? And the honest answer, the scientifically honest, data-informed answer, is that we do not know. But we have reasons to be concerned. We have already established that this region produced M-class flares on 2 separate occasions in 3 days, and that the second event was significantly stronger than the first. We have established that it was already active before it was even visible to Earth, suggesting a deep and pre-organized magnetic structure. We have established the possibility of continuous flux emergence that could sustain or increase activity rather than allowing it to wind down. Against that background, the optimistic scenario that the region quietly decays over the next several days and arrives at central meridian as a spent, quiescent structure is not supported by any particular trend in the data we have seen so far. The pessimistic scenario is worth stating plainly. A region that has been escalating, that has a history of strong flares going back to before it was even visible, that may be continuously fed by subsurface flux emergence. That region, when it reaches the geoeffective window on roughly May 13th, could produce another M-class or potentially X-class flare. A CME from that position, at 650 km per second, would arrive at Earth approximately 1 to 3 days after eruption. The warning time between the eruption and the arrival of the plasma cloud is not large. It is enough time to issue alerts, to prepare sensitive systems, to remind satellite operators that they may want to put spacecraft into safe mode. It is not enough time, in any meaningful sense, to do anything structural about infrastructure vulnerability. And here is the part of the timeline that I want you to really sit with. The CME we watched on May 10th, the 650 km per second event that produced an R2 radio blackout and all the multi-signal confirmation we have been discussing, arrived at whatever patch of interplanetary space it was aimed at in roughly 1 to 2 days. If a similar event occurs when the region is near central meridian on May 14th or 15th, that same travel time applies to Earth. You would have perhaps 36 to 48 hours of warning between seeing the flare and experiencing the geomagnetic consequences. During solar maximum conditions, when active regions can produce multiple CMEs in quick succession, that warning time can compress further if a faster second CME catches and merges with a slower first one on the way to Earth. The narrowing gap between watching the eruption and responding to the arrival is one of the fundamental challenges of space weather forecasting. We're not in a situation where we can simply wait and see what the region does when it arrives at optimal geometry. By the time it arrives, the next eruption could be hours or days away. The observation window, the prediction window, and the reaction window all overlap in uncomfortable ways. There is not a clean sequence of see it, predict it, prepare. There is a scramble of real-time monitoring against a clock that is ticking at 13 degrees per day. What we are watching right now in real time is that clock. Part 6. Born Complex. The regions that arrive ready. To understand why active region 4436 behaves the way it does, you need to understand something about what happens beneath the surface of the Sun, in a region we cannot directly observe but whose effects we're watching play out across the solar disk right now. The Sun's visible surface, the photosphere, is the ceiling of a convection zone that extends roughly 200,000 kilometers below it. In that convection zone, massive columns of hot plasma rise, cool and sink in churning circulation patterns that carry not just heat but magnetic flux. The magnetic field lines that will eventually break through the surface and form sunspot regions start deep in this zone, winding and twisting as they are carried by differential rotation and convective flows. By the time they are ready to break through, they carry the magnetic structure they accumulated during that underground journey. Most sunspot groups emerge from this process relatively gradually. The flux breaks through in a bipolar configuration, positive polarity here, negative polarity there. And the complexity builds over days as more flux continues to emerge and the existing field lines interact and tangle. Forecasters can watch this process in near real time through magnetogram imagery that shows the distribution of positive and negative magnetic polarity across the solar surface. They can see a simple bipolar region developing, can track the growth of complexity, and can adjust their probability forecasts accordingly. There is a rhythm to it. There is a developmental timeline that, while variable, gives some predictability. Born complex regions do not show that developmental timeline, and this brings us directly back to where we are today with active region 4436. They arrive at the surface already carrying a magnetic configuration that normally takes days to develop. This suggests the organization happened underground, that the flux rope or magnetic structure that eventually breaks the surface was already wound tightly and tangled before emergence. It is a region that has already done its homework before showing up to class. The implication for flare forecasting is significant. The standard probability estimates that space weather centers publish are based partly on observed magnetic complexity at the time of assessment. A region with a simple magnetic configuration gets a low flare probability. A region with complex mixed polarity magnetic field lines in close proximity gets a higher probability. But born complex regions can arrive at the surface with already high complexity immediately jumping to elevated flare probability before forecasters have had a chance to see the development process unfold. And if the assessment is made at a point before the full complexity is visible, for example when the region is still partially behind the limb, the forecast probability can significantly underestimate the actual risk. Active region 4436 produced an M-class flare before it was fully visible. Before a complete assessment of its magnetic structure was even possible, it was already producing events that exceeded the expected output for a region of its classified size. That is a Born complex region doing exactly what Born complex regions do, skipping the developmental curve and going straight to energetic output. And it tells us something important about the energy budget of this region. Whatever is stored in that magnetic structure was not built up over the few days since emergence. It was carried here from below. That energy has been available for release since before we first saw the region. And based on the escalating flare history, M2.6 followed by M5.7, it has not all been released yet. This is why the rotation timeline matters so much. Not just because the geometry is changing, but because the energy source is not depleted. The region that arrives at central meridian in 4 to 5 days is not the spent remnant of a system that released its stored energy at E65. It is, based on the evidence available, a system that has been producing flares while building toward the position where those flares would actually matter for Earth. Part 7. The Far Side Warning Signal. Let us go back to May 7th, because that date is more important than it might first appear, and what it represents is a kind of warning that arrived before anyone was fully ready to receive it. On May 7th, active region 4436 was at approximately east 90, right at the solar limb partially behind it, visible from Earth only as the very top of its corona peeking above the edge of the Sun's disk. Standard solar imaging at that position can tell you that something is there. It cannot tell you much about its magnetic configuration, its spot structure, or its detailed complexity. The region is essentially a silhouette of itself at that longitude. What you can detect are the most energetic phenomena, flares powerful enough that their X-ray signature bleeds around the limb, radio bursts from shocks propagating high into the corona, and sometimes coronagraph imagery of CMEs lifting off from behind the edge. On May 7th, with the region in that partially hidden position, it produced an M2.6 flare. Think about what that means. In order to produce an M2.6 classification, the X-ray flux from that region had to be strong enough to register above the background emission of the entire Sun combined. Solar X-ray detectors measure integrated full-disk X-ray output. When a flare produces an M-class event, it is bright enough to noticeably elevate the total X-ray output of the Sun from a region that, at that moment, we could barely see. The X-rays had to propagate outward and around the limb of the Sun to reach our detectors. The event was, by any reasonable standard, significant, and the region was still in its hidden approach phase. In space weather forecasting, behind the limb flares function as an early warning signal. They tell you a region is coming and they give you a preview of its behaviour. They do not tell you how the region will evolve over the coming days, or whether the activity will increase, decrease, or plateau. But they establish a baseline. They tell you, this region was producing M-class events before we could even fully observe it. Treat accordingly. The gap between May 7th and May 10th, the transition from M2.6 behind the limb to M5.7 at E65, covers 3 days of increasing visibility and escalating output. That is a trajectory that goes in one direction, and the question that forecasters are now trying to answer, with incomplete data and limited observation time before the geometry becomes critical, is whether that trajectory continues, flattens, or reverses over the next 4 to 5 days as the region moves into the geo-effective window. The honest answer, again, is that we cannot know with certainty. Solar flare forecasting is not like weather forecasting, where the underlying physics, fluid dynamics, thermodynamics, can be modelled in high-resolution computational simulations with reasonable skill. Solar flare forecasting still involves substantial uncertainty at the level of individual event timing and magnitude. We can characterise probability. We can say this region has a 30% chance of producing an M-class flare in the next 24 hours, with some statistical validity. What we cannot say is, the next flare will occur on May 14th at 0900 UTC and will reach M6.2. The physics is too nonlinear. The triggering mechanisms are too sensitive to initial conditions we cannot directly measure. What we can say is that the pattern established by active region 4436, active before visibility, escalating intensity, born complex magnetic structure, is not the pattern of a region in its quiet final phase, and every day of rotation brings the consequences of being wrong about that closer to Earth's doorstep. Part 8. Competing models for what comes next. Here is where the science becomes genuinely uncertain in ways that should probably make you a little uncomfortable, because this is the point at which forecasters have to commit to a model of what active region 4436 is actually doing, and multiple models are consistent with the data. The first model is what you could call sympathetic flaring, or cascade triggering. In this scenario, the M2.6 event on May 7th disturbed the magnetic equilibrium of nearby field lines, producing conditions favourable for a subsequent release. The M5.7 on May 10th was, in this model, partly triggered by the destabilisation caused by the earlier flare, not an independent event but a downstream consequence of the first one. If this model is correct, then May 10th's flare may have partially reset the region's energy balance. The cascade completed, the stress was partially relieved, and the region may now be in a relative minimum of instability. This would be the more optimistic interpretation. The second model is energy depletion. Large flares release stored magnetic energy, and in some regions, a sufficiently large release permanently or semi-permanently reduces the complexity of the field configuration. The stressed magnetic geometry that made flaring possible is relaxed by the release itself, and the region moves into a quieter, more stable state. Under this model, the M5.7 on May 10th may actually represent the peak of the region's activity. The big event happened, the stress was released. What arrives at central meridian passage may be a weaker post-eruption structure significantly less capable of further major events. The third model is continuous flux emergence. In this model, the magnetic complexity of active region 4436 is not a fixed reservoir being gradually depleted with each event. New flux is continuously rising from below, replacing and potentially exceeding what was released in previous flares. Under this model, the region is not winding down, it is being refueled. Each event represents a local release of the most concentrated stress, but the underlying magnetic infrastructure keeps rebuilding and keeps producing new gradients where energy can accumulate and eventually release. Now, how do we distinguish between these models with the data available? Magnetogram time series, observations that track the evolution of magnetic polarity patterns across the sunspot region over time, are the primary diagnostic tool. If the total magnetic flux in the region is decreasing after the May 10th event, energy depletion is consistent. If it is increasing, continuous emergence is the more likely explanation. If it fluctuates in a pattern consistent with repeated partial releases and partial recoveries, sympathetic cascade becomes more plausible. The problem is observation time. The region has been fully visible for only a few days. 3 days of magnetogram data is not a long baseline for distinguishing between these models with confidence. And the critical window, the point at which the model distinction matters most when the region enters the geoeffective zone, opens before we will have accumulated enough time series data to feel confident in any single interpretation. This is the texture of real-time space weather forecasting, not clean answers from a well-characterized system, competing models, insufficient data, and a timeline that demands a working interpretation before the data is sufficient to support one definitively. Forecasters make probabilistic judgments under these conditions every day. They are by and large remarkably good at it. But even the best probabilistic judgment leaves a meaningful chance of being wrong in the direction you least want. And the direction you least want in this case is the third model, continuous emergence, sustained activity, an energetically fresh region arriving at central meridian with the same or greater flare potential than it showed on May 10th. That is the scenario we're going to spend some time examining in detail. Part 9. The historical analogue, Region 9.3. History does not repeat, but it does sometimes send very pointed reminders. In March of 2001, the Sun was in a part of solar cycle 23 roughly analogous to where we sit today in cycle 25, past the peak, in the declining phase, but still producing significant active regions with flare histories that surprised forecasters. Active region 9393 was one of those regions. It was rotating across the solar disk during the middle weeks of March 2001, and its behaviour established a pattern that should feel familiar. It was active before central meridian. It produced significant flares, including events that were clearly energetic before the region reached optimal Earth-facing geometry. And when it did reach central meridian, the eruptions it produced were among the strongest of that solar rotation. The analogy is not predictive. Saying that region 9393 behaved a certain way in March 2001 does not tell us that active region 4436 will behave the same way in May 2026. The Sun is not reading from a script, and individual active regions are as individual as anything in nature. The magnetic structure, the subsurface conditions, the specific configuration of surrounding field lines, all of these factors vary, and the variation matters. What the analogy does provide is context for the general pattern. Regions that are active on approach to central meridian have a documented history, in multiple solar cycles, of continued activity through the Earth-facing window. The behind-the-limb and early limb flares are not necessarily a preview of a system on its way out. In many historical cases, and region 9393 is one example, they were a preview of a system on its way up. The big events came not before the geo-effective window but during it. The approach phase was an escalation, not a release. That is the pattern we are watching for with active region 4436. Not with certainty, not with the confidence of a prediction, but with the awareness that historical analogues from comparable phases of comparable solar cycles do not offer comfort to the optimistic interpretation. They offer motivation to take the pessimistic interpretation seriously. And taking the pessimistic interpretation seriously means thinking carefully about what a direct hit from this region would actually look like. That is the next part of this story. Part 10. The Silent Giant on the Same Disk. While active region 4436 has been commanding attention with its escalating flare history, there is another region on the solar disk that, on paper, should be the one we are worried about. The fact that it is not, the fact that it has been sitting quietly while the smaller, less classified region has been doing the alarming things, is itself a lesson about the limits of solar forecasting, and it adds a complicating layer to the risk picture for the next several days. Active region 4432 is the region in question. Its numbers look nothing like 4436, area coverage of approximately 430 millionths of a solar hemisphere, nearly 3 times larger, 28 visible sunspots compared to 6, magnetic classification that includes beta-gamma complexity, the classification range where the positive and negative polarity fields are sufficiently mixed that energy release conditions are much more readily met. The Space Weather Prediction Center's probability forecasts for this region have been consistently higher than those for 4436. By the standard metrics, this is the one that should have already done something notable, and yet through the period when active region 4436 was producing M-class events from behind the limb, and then again at E65, 4432 was producing C-class flares, the small stuff, the events that barely clear the threshold of notice, that produce minor or negligible geomagnetic responses, that are logged and filed and not discussed in any video with an alarming title. There are several explanations for this, and none of them are definitively correct. One possibility is that 4432 is experiencing gradual energy release, small events bleeding off the stored magnetic stress in a relatively controlled, incremental way that prevents the buildup of the extreme gradients needed for a major flare. This is actually a recognized phenomenon. A region that flares frequently in small ways may be actively preventing the energy accumulation that produces big events. The continuous small releases act as pressure valves, keeping the system below the threshold for catastrophic discharge. Another possibility is that the magnetic configuration, despite its apparent complexity, is currently in a relatively stable arrangement, a metastable state where the field lines are tangled but not in a way that makes reconnection easy. Magnetic complexity on a magnetogram looks alarming, but not all complex configurations are equally unstable. Sometimes a region needs an external trigger, an emerging flux event, a nearby eruption from another region, a simple evolutionary shift in the field configuration to push it from metastable to unstable. What this means in the context of the central story is that the solar disk over the next several days carries not just one potentially problematic active region, but 2. Active region 4432 sites in the western hemisphere of the solar disk, past central meridian moving away from optimal Earth-facing geometry, but still within the geo-effective window for some portion of its remaining transit. If it produces a major flare in CME in the coming days, while active region 4436 is simultaneously active during its approach and central meridian passage, the scenario becomes considerably more complicated than a single eruption event. Multiple CMEs in close succession create conditions that the standard single event impact models do not fully capture. The interaction between sequential plasma clouds in the interplanetary medium is one of the most unpredictable aspects of space weather forecasting, and it is also one of the most potentially consequential. We are going to spend considerable time on that specific scenario later in this video. For now, simply note that the solar disk currently carries two active regions capable of significant events, arriving at optimal Earth-facing geometry on overlapping or closely spaced timelines. The risk picture is not a single point estimate. It is a distribution, and the upper tail of that distribution has been receiving uncomfortable attention from the forecasting community. Part 11. The Quiet Sun. That wasn't Air 4432's silence. The quiet from active region 4432 deserves its own examination, because the absence of expected behavior in a high probability region is itself a piece of data, and it can be interpreted in more than one way. The most optimistic reading is that 4432 is simply declining. Large sunspot regions do eventually exhaust their complexity through a combination of gradual energy release, magnetic field dispersion, and the natural decay of the photospheric flux concentrations that form the spots themselves. If the region is in an advanced decay phase, its C-class flare output may reflect not stored energy awaiting release, but the final, diminishing activity of a system that has already passed its peak. In this scenario, 4432 is less relevant to the next week's space weather than its size would suggest. The more unsettling reading is that the silence represents stored energy rather than depleted energy, a region that has been building complexity, accumulating stress, experiencing the gradual coalescence of magnetic polarities toward the configuration that enables major events, and has not yet found the trigger to release, is not a quiet region in any meaningful sense. It is a loaded one, and a loaded region that has not yet fired is not safer than one that has been actively flaring. In some assessments, it is more dangerous, because the energy budget has not been partially depleted by intermediate events. The concept of stored but unreleased energy has appeared in post-event analyses of some of the most significant solar storms in the modern observational record. Regions that appeared to be winding down or stabilizing produced unexpectedly large events, because the apparent quiet was concealing the continued organization of a highly stressed magnetic configuration. The flare, when it came, was not preceded by obvious warning signals of increasing activity. It came from a system that looked, until moments before, like it was done. None of this means active region 4432 is about to produce an X-class flare. The uncertainty runs in all directions, but the combination of its size, its magnetic complexity classification, its current location in the geo-effective window, and its unexplained silence creates a set of conditions that forecasters cannot simply file under "not a concern." It is a complicating factor in an already complicated picture, and it underscores a theme that this video keeps returning to from different angles. The solar disk right now carries more uncertainty than usual, and the uncertainty is concentrated in the next 4 to 6 days. The same window during which active region 4436 arrives at central meridian, 4432 is still within range to contribute to the geomagnetic environment. Two potentially active regions, one approaching optimal geometry, one of unexplained silence in a high complexity configuration. The overlap is not something you can reassure yourself out of. Part 12. What would have happened if this hit us? Let us build the scenario we narrowly did not have to experience, because it is directly relevant to what might be coming, and it establishes the baseline against which the next event will be measured. The May 10th CME had an estimated speed of 650 km per second. That is fast. The average CME speed is closer to 400 to 500 km per second, but it is not at the extreme end of the distribution. The fastest CMEs on record have exceeded 2,000 km per second. What we're dealing with here is a meaningfully above average event, not a record breaker, but not in the comfortable middle of the speed range either. For a CME at 650 km per second with this flare event profile, the expected geomagnetic storm classification upon direct Earth impact would most likely fall in the G1 to G2 range, minor to moderate. The current G scale runs from 1 to 5, with G5 representing the extreme events like the Carrington event of 1859 or the Halloween storms of 2003. A G1 to G2 impact is real but manageable. It produces auroral visibility at high to mid-latitudes. It can cause minor fluctuations in power systems, particularly those near high-latitude geomagnetically induced current exposure zones. Satellite drag increases, requiring orbit maintenance corrections. High-frequency radio experiences temporary disruptions at higher latitudes. GPS accuracy degrades modestly. None of these are civilization-scale consequences on their own. For direct comparison, the G2 storm that affected Earth on May 4, 2026, just 6 days before the event we are discussing, produced exactly these kinds of effects. Auroras were reported across northern and central latitudes. A handful of satellite operators noted increased drag. Radio operators noted propagation anomalies. The power grid held, society continued. The G2 threshold is the kind of event that makes enthusiastic aurora chasers very happy and infrastructure operators mildly busy. But there is a variable that changes all of this, and it does not get nearly enough attention in popular coverage of solar weather. The variable is the orientation of the interplanetary magnetic field, specifically a component called bees. The interplanetary magnetic field is not uniform. It has direction and it fluctuates, carried on the solar wind and embedded in the plasma of coronal mass ejections. The bees component is the north-south orientation of this field. When bees is pointing southward, opposite to the direction of Earth's magnetic field at the dayside magnetopause, the two fields couple efficiently. The solar wind plasma can transfer energy into Earth's magnetosphere much more effectively, driving geomagnetic currents, energizing the radiation belts, and producing the kind of sustained intense storm that causes real infrastructure consequences. When BES is pointing northward, the opposite happens. The fields align, coupling is suppressed, and even a fast, dense CME can arrive at Earth and produce a much weaker storm than its kinematic parameters would suggest. A fast CME with northward BZ can feel like a non-event. A moderate CME with strongly southward BZ can feel like a catastrophe. The speed and density of the CME tells you the maximum potential severity. The B's orientation tells you how much of that potential actually gets delivered. And the maddening truth about B's is that we cannot reliably predict it until the CME arrives at the L1 Lagrange point, a location about 1.5 million kilometers sunward of Earth, roughly 15 minutes to an hour of solar wind travel time upstream of the magnetosphere, depending on solar wind speed. At that point, the ACE and Discover spacecraft measure the actual magnetic field orientation of the arriving plasma, and forecasters finally know whether BES is cooperating or not. 15 minutes to 1 hour. That is the advance warning time for the most important variable in the entire impact calculation. Everything before that point is probability distributions, model runs, and educated extrapolation. So the honest version of the what would have happened scenario for May 10th is probably a G1 to G2 event, with a non-trivial chance of escalation if the CME carried sustained southward BES, and a smaller but non-zero chance of remaining below G1 if BES was consistently northward throughout the event. The most likely outcome was moderate and manageable. The tail risks sought in both directions were not negligible, and the same analysis applies to whatever active region 4436 produces when it reaches central meridian, but with a complication. Part 13. The real risk. When CMEs meet each other. There is a scenario in space weather that forecasters have a specific word for, and hearing that word in a forecast discussion is one of the things that makes experienced space weather operators sit up straight. The word is cannibal. A cannibal CME is not a metaphor about the sun consuming itself. It refers to a specific and genuinely concerning phenomenon that occurs when a second, faster CME is launched from a solar active region and catches up with an earlier, slower CME on the way to Earth. In the interplanetary medium between the Sun and Earth, two plasma clouds collide and merge, with the faster one overtaking and absorbing the slower one. The resulting combined structure, the cannibal, has a magnetic field that is the product of two separate eruptions interacting and amplifying each other. The consequences of a Cannibal CME impact are not simply the sum of two moderate events. The interaction between the two plasma clouds can produce magnetic field enhancements significantly stronger than either cloud would have carried individually. The merge field structure can maintain sustained southward B's orientation for longer than a single CME event typically would, and the compressed region at the leading edge of the merger can carry particularly elevated density and magnetic field strength. In practical terms, a Cannibal CME event can escalate what would have been two G2 impacts into a single G4 or G5 impact. The interaction is not additive, it can be multiplicative. This matters directly to the situation with active region 4436 because of the region's demonstrated flare cadence. Two M-class events in 3 days, with an escalating intensity profile, suggest this is a region capable of multiple eruptions in close succession. If the region produces two CMEs within 24 to 48 hours of each other, while in the geo-effective window, a scenario that is entirely consistent with its recent behaviour, and if the second CME is faster than the first, the Cannibal scenario becomes physically plausible. The probability of any specific version of this scenario is not high, but the key word is specific. The probability that at least one significant CME arrives during the active region 4436 Earth-facing window is considerably higher than the probability of any individual event, and the probability that a sequence of CMEs could interact in ways that amplify their combined effect. That is not a negligible tail risk given the demonstrated cadence of this region. Historical examples exist. The Halloween storms of October and November 2003 included sequences of fast CMEs in close succession, with compound effects that produced G5 geomagnetic storm conditions, widespread power grid disruptions in Sweden, and satellite anomalies numbering in the dozens. The September 2017 events included a Cannibal CME sequence that elevated storm intensity beyond what single event modelling predicted. These are not theoretical scenarios. They are documented meteorological records of what happens when the Sun produces multiple fast eruptions in quick succession at favourable geometry. Active region 4436, moving towards central meridian with a demonstrated pattern of escalating repeated M-class events, presents the conditions for this scenario to be physically possible during the watch window. That does not mean it will happen, but it means the conversation about what could happen in the next week is not a conversation about G1 to G2 baseline events only. It is a conversation about the realistic upper end of a distribution that extends further than the baseline. Part 14. Modern Fragility. The Starlink Lesson. In February of 2022, a relatively minor geomagnetic storm made headlines not for the power grid disruptions or radio blackouts that typically define memorable space weather events, but for destroying 40 satellites. The G1 event, the lowest classification on the storm scale, the kind that Aurora apps send push notifications about, coincided with a batch of Starlink satellite deployments. SpaceX launches new satellites to low Earth orbit in groups, and newly deployed satellites spend their first days at lower altitudes while their onboard systems check out and their ion thrusters gradually raise them to operational orbit. During a G1 storm, the upper atmosphere expands slightly as it absorbs the increased energy input from the solar wind. This expansion, invisible, unfelt at ground level, barely noticeable on any instrument most people would ever interact with, increases the density of the atmosphere at low orbital altitudes. And for a freshly deployed satellite coasting at the edge of the atmosphere, that slight density increase translates to increased drag. More drag means more orbital energy loss. More orbital energy loss means lower orbit. Lower orbit means more drag. 38 of the newly deployed Starlink satellites entered a positive feedback loop that their systems could not arrest. Their thrusters could not compensate for the increased drag fast enough to maintain orbit. One by one, over the days following the storm, they decayed into the upper atmosphere and burned up. 38 satellites from a G1 event. The Starlink incident is not relevant to the active region 4436 story, because it suggests that the next solar storm will destroy satellites in bulk. The context was specific, newly deployed, low altitude, in checkout mode with limited thrust authority. Operational satellites at higher altitudes are much more resilient. The lesson is something more subtle and more broadly applicable. The lesson is that modern technological infrastructure interacts with space weather in ways that are not fully captured by the headline storm classifications. A G1 is supposed to be minor effects on satellite operations. The Starlink event produced a loss of infrastructure worth hundreds of millions of dollars from a G1 event because the specific circumstances, the altitude, the operational mode, the deployment timing, created a vulnerability that the generic classification did not capture. We have populated the near-Earth space environment with tens of thousands of satellites over the past decade. Many of them operate in low or medium Earth orbit. Many of them provide services, navigation, communications, Earth observation, that are now embedded in the infrastructure of global logistics, emergency response, and financial systems in ways that were not true even 5 years ago. A space weather event that produces minor satellite effects at the classification level can produce significant infrastructure consequences at the dependency level, because the infrastructure that depends on those satellites is not the same infrastructure that existed when the classifications were designed. If active region 4436 produces Earth-directed CMEs during the next week, the baseline scenario, G1 to G2, manageable effects, remains the most likely outcome. But the distributional tail and the Starlink-style specific circumstance vulnerabilities that do not show up in the headline storm number deserve to be part of the conversation. Part 15. The pattern of quiet before impact. There is something almost theatrical about the current space weather conditions around Earth as we record this. The K-index is sitting near 2. Solar wind is flowing at a quiet 400 kilometers per second. The interplanetary magnetic field is weak and variable. There are no geomagnetic storm watches or warnings in effect. By every metric that operational forecasters use to characterize the near-Earth space environment, the situation right now is about as quiet as it gets during an active phase of the solar cycle. The magnetosphere is undisturbed, the radiation belts are in their baseline state. The auroras are staying politely within the polar circles. This is not a coincidence. It is the precise condition that precedes many significant space weather events, not because quiet conditions cause eruptions, but because eruptions are not continuous. The sun does not produce a steady stream of major events. It builds and releases, with the quiet periods representing the accumulation phase and the active periods representing the release phase. We are right now in an accumulation phase at the most interesting possible moment, with an active region that has already demonstrated release capability rotating into position for Earth-directed release. There is a concept in dynamical systems called critical transitions, where a system that has been building stress in a relatively stable configuration undergoes a rapid shift to a new state. The transition is not gradual, the system resists until it does not, and then the change is fast. In solar physics, flares are exactly this kind of critical transition. The magnetic field builds stress over hours or days. The configuration resists reconnection until the gradient exceeds a threshold, and then the energy releases on timescales of minutes. The quiet before the event is not a sign that nothing will happen. It is in many cases the signature of a system still building toward its threshold. The current quiet around Earth reflects the fact that active region 4436's recent eruptions were not directed at us. They went somewhere else and disturbed some other part of the heliosphere. The energy was released, but we were not in the path. The geomagnetic environment is undisturbed because it was not the target. And as the region rotates toward us, the energy that will power the next eruption, whatever form it takes, is following its own timeline, indifferent to ours. What makes this quiet period worth paying attention to is precisely its contrast with what it could soon become. The transition from KP2 to KP5 or 6 is not a gradual one. It can happen within hours of a CME arrival. The 36 to 48 hour travel time from Sun to Earth, combined with the roughly 1 hour of B's measurement time before impact, means that the geomagnetic environment can go from today's undisturbed baseline to full storm conditions in a single operational shift. The quiet you're sitting in right now is not a promise about tomorrow. It is a baseline reading before the experiment has started. Part 16. Solar cycle context. Where we are in the pattern. Solar cycle. 25 has been one of the more interesting chapters in the modern space weather record, for reasons that have a direct bearing on understanding what we are watching now. When the cycle began its rise around 2019 and 2020, the consensus forecast from the solar physics community was for a modest, below-average cycle, comparable to the weak cycle 24 that preceded it, itself one of the weakest in a century. The models, the statistical extrapolations, the ensemble forecasts all pointed toward a cycle that would be unremarkable in terms of maximum sunspot number and major event frequency. What actually happened was substantially different. Cycle 25 tracked well above the consensus forecast during its rising phase, achieving a sunspot maximum that exceeded pre-cycle predictions significantly. The years 2023, 2024, and 25 delivered a sequence of significant space weather events, including the May 2024 geomagnetic storm that reached G5 conditions and produced auroras visible across middle latitudes worldwide that were more consistent with the historical behavior of above-average cycles than the below-average cycle the models had predicted. This overperformance matters for interpreting the current situation because it tells us something about what this cycle is capable of, even in its declining phase. Cycle 25 is past its sunspot maximum. The overall trend in solar activity is, on a multi-month timescale, downward. But declining phase activity in an above-average cycle is not the same as declining phase activity in a weak one. Some of the most significant individual events in solar cycle history have occurred during the declining phase. The Halloween storms of 2003 occurred during the decline of cycle 23. The February 2004 X6.9 flare, one of the strongest on record, occurred well past that cycle's maximum. The declining phase of an active cycle is not a quiet epilogue. It is a continuation of the story, with episodic chapters that can still include major events. Active region 4436 is emerging during exactly this phase, the declining portion of an above-average cycle that has already demonstrated its capacity for surprising the models. The region itself is already behaving unexpectedly relative to its classified parameters, and the geometric conditions that will make its behavior either matter or not matter for Earth are unfolding over the next 4 to 6 days, within what is still statistically an active period of an active cycle. The broader cycle context does not predict what any specific active region will do, but it establishes the environment in which that region is operating. And the environment is one where the background expectation that the cycle's most dramatic moments are in the past has already been proven wrong before, in this cycle, more than once. Part 17. Alternative narratives and the misconceptions worth addressing. At this point in the video, some of you are probably encountering the alternative interpretations that circulate whenever solar activity makes the news. The claims that data is being suppressed, the theories about artificial influence, the assertions that solar events are connected to earthquakes and other terrestrial phenomena. These ideas spread quickly in the online space weather community, and they deserve to be addressed directly, not to dismiss the people raising them, but because the truth is actually more alarming than the fiction, and understanding the difference matters. On the question of hidden data, the solar monitoring infrastructure is genuinely one of the most transparent scientific systems in existence. The Space Weather Prediction Center publishes real-time data continuously, accessible to anyone with an internet connection. The data from GOES satellites, from the ACE and Discover solar wind monitors, from ground-based magnetometer networks, all of it streams publicly, updated every few minutes. The community of amateur solar observers who cross-check official readings against their own instruments numbers in the thousands. The academic space physics community worldwide, with no reporting relationship to any government agency, publishes independent analyses. The idea that the kind of coordinated suppression required to hide a significant solar event could be maintained across this ecosystem is not consistent with how the ecosystem actually works. What does get missed is not hidden data. It is the rotation. The whole story of active region 4436, the alarming story, is visible in the public data. The M5.7 at East 65, the M2.6 from behind the limb, the trajectory towards central meridian, the multi-signal confirmation of event strength. All of it is sitting in openly published SWPC bulletins, available online, time-stamped and detailed. The reason most people do not know about it is not suppression. It is that nothing alarming happened to Earth today, and alarming thing happened to the Sun but aimed away from us is not the kind of headline that breaks through the noise. The real story is the rotation. And the real story is in the public record on the question of artificial influence. Specifically the recurring claim that facilities like HARP or other ionospheric research installations are somehow capable of influencing solar activity or directing solar eruptions. The energy scales involved make this claim physically impossible, in ways that are not ambiguous. The total power output of HAARP's transmitter is on the order of 3.5 megawatts. An M5.7 solar flare releases energy on the order of 10 to the 32nd power ergs, many orders of magnitude beyond the total energy budget of every power plant on Earth combined, let alone a single research installation in Alaska. There is no mechanism by which a facility operating at human engineering scales interacts with processes occurring on stellar scales. The Sun is not responding to us. We are not significant enough energetically to be part of that equation. The events we are discussing are purely the product of magnetic physics operating on a star 109 times the diameter of Earth. We are, in this story, the bystanders. On the question of solar terrestrial connections to seismic activity, this one is worth a brief careful treatment because it has a more complicated scientific status than the others. There are published studies that report statistical correlations between solar activity and seismic event frequency. The correlations are real in some analyses, and weak but not zero. The problem is that correlation without mechanism is not a causal relationship, and no physically plausible mechanism has been established by which geomagnetic disturbances of the magnitudes we are discussing would trigger earthquakes. The lithospheric stresses that cause earthquakes are orders of magnitude larger than anything the geomagnetic variations produced by solar storms could plausibly influence. The correlations, where they appear, may reflect common underlying periodicities or statistical artifacts. They do not establish that a solar event on one day should be expected to produce a seismic event on the next. The real risk from the events we are discussing is space weather, radiation, geomagnetic storms, satellite disruption, radio blackouts, and that risk is well established, well characterized, and right now directly relevant. The speculative terrestrial connections are a distraction from the story that actually matters. And the story that actually matters is that a Born-complex escalating sunspot region is rotating toward Earth-facing geometry on a timeline that closes in 4 to 5 days. Part 18. The rotation timeline, degree by degree. Let us walk through the next 4 to 6 days in specific terms, because precision matters here, and I want you to have a clear mental picture of how the situation evolves. On May 10th, today, the day of the M5.7 event, active region 4436 is at approximately East 65. Eastern limb territory, clearly outside the geo-effective window of East 30 to West 30, aimed well away from Earth. Any CME produced at this longitude has a high probability of missing Earth entirely, as May 10th demonstrated. On May 11th, the region will be near East 52, still outside the geo-effective window but approaching its edge. A very wide CME, or one from the upper range of angular widths, could potentially clip Earth's magnetosphere with a glancing blow from this position. The probability of direct impact remains low, but it is no longer zero. On May 12th, the region will be near East 39, within a day's rotation of the formal outer edge of the geo-effective window. A fast, wide CME from this position has a meaningful probability of producing at least a minor geomagnetic storm impact. Forecasters begin moving this into elevated watch territory. On May 13th, near East 26, inside the geo-effective window. Any CME from this position, at the speeds active region 4436 has demonstrated, produces a realistic probability of Earth impact. Travel time at 650 km per second from this position is approximately 1 to 1.5 days. A flare on May 13th means potential storm arrival, May 14th or 15th. On May 14th, near East 13, well inside the geo-effective window, approaching central meridian. Maximum risk position. Any CME from this longitude is heading approximately in Earth's direction. Travel time is approximately 1 to 1.5 days depending on speed. On May 15th or 16th, central meridian passage or near it, optimal geo-effective geometry. This is the maximum risk position. A CME produced here arrives at Earth in approximately 1 to 2 days, with the trajectory directly aimed at the magnetosphere. After central meridian, the region begins moving into western longitudes and eventually exits the western edge of the geo-effective window. The western positioned CMEs can still produce significant impacts because the Parker spiral geometry of the interplanetary magnetic field actually favours slightly western source locations for well-connected events. The entire risk window, the period during which active region 4436 could produce Earth-directed events, spans approximately May 13th through May 20th. The highest risk subwindow centered on Central Meridian Passage is May 14th through 16th. That is 96 to 144 hours from now. What forecasters are watching during this window is not just whether flares occur, they are watching the flare cadence, how frequently events are occurring and whether the frequency is increasing or decreasing. They are watching the magnetogram evolution, whether the magnetic complexity is building, stable or declining. They are watching for signs of flux emergence, brightening in ultraviolet wavelengths that can indicate new magnetic flux pushing through the photosphere and adding to the region's energy budget. They are watching the coronagraph imagery for any CMEs that emerge from the region's disposition, and tracking those CMEs carefully to determine trajectory, speed, and potential Earth arrival. All of this watching, all of this monitoring, it is continuous, and it is happening right now, not in a simulated scenario or a forecast exercise, in real time, because the window is open and the timeline is running. Part 19. What scientists are watching, the specific indicators. Let us be specific about the diagnostic signals that will tell forecasters, and through them, infrastructure operators, satellite controllers, and emergency management agencies, what active region 4436 is going to do. The most immediate and continuously updated signal is flare cadence. The frequency and strength of flares from a region is not random noise. It reflects the evolving state of the magnetic field. A region that is producing M-class events every 24 to 48 hours, as active region 4436 has been doing, is demonstrating a cadence that forecasters use to calibrate their near-term probability estimates. If that cadence accelerates, if the gap between events shortens, or if the event magnitudes increase, it suggests the region is entering an increasingly unstable state. If the cadence slows, if the region goes 24, 48, 72 hours without a significant event, it may indicate the stress is releasing slowly or the field configuration is stabilizing. The second key diagnostic is the evolution of magnetic complexity, as measured by continuous magnetogram imaging. The GONG network, Global Oscillation Network Group, provides round-the-clock full-disk solar magnetograms from ground-based observatories distributed around the world, ensuring that no part of the solar disk goes unobserved due to Earth's day-night cycle. These magnetograms show the distribution of positive and negative magnetic polarity across the photosphere with regular cadence. Forecasters are watching active region 4436's magnetogram evolution closely for signs of increasing complexity, the mixing and shearing of opposite polarity fields that produces the gradient conditions most favourable for major flares. Third, and more subtly, the ultraviolet and extreme ultraviolet emission profiles from the region. The SDO, Solar Dynamics Observatory, continuously images the Sun in multiple ultraviolet and UV wavelengths, and these images reveal the structure and evolution of the corona above active regions. Brightening in certain UV wavelengths can indicate flux emergence, new magnetic field pushing through the photosphere and into the corona, adding to the region's energy budget. Persistent or increasing UV brightness in the region suggests ongoing activity of the underlying magnetic system. Fading and dimming suggests the region is winding down. Fourth, coronagraph imagery from SOHO and stereo, watching for partial or full halo CMEs. A full halo CME, a plasma cloud that, when imaged by a coronagraph, appears as a ring expanding in all directions around the Sun, is the signature of an Earth-directed event. Not perfectly predictive, but a major alert signal. A partial halo or asymmetric halo expanding toward the Earth's position is equally important. Coronagraph imagery has a time cadence of roughly 12 to 24 minutes for major instruments, meaning a CME can be detected and initially characterized within an hour of launch. The trajectory is less certain at launch than at the L1 point, but the earliest coronagraph detections trigger the cascade of forecasting and alert procedures. Fifth, particle data from ACE and DSCOVA, the twin solar wind monitors sitting at the L1 point between Earth and the Sun. As a CME approaches, these spacecraft measure the solar wind speed, density, and magnetic field in real time. The approach of a CME is visible in the particle data as a density enhancement, and often a speed jump, the bow wave arriving ahead of the main plasma structure, and crucially, the first measurements of B's orientation, the critical variable that determines how strongly the arriving CME will couple with Earth's magnetosphere, come from these spacecraft. By the time the B's measurement is in hand, Earth impact is typically 15 to 60 minutes away. That is the actual operational forecast timeline for the most important variable. Not days, not hours, minutes. This is the infrastructure watching what active region 4436 does next. It is remarkably capable, continuously operational, and staffed by professionals who understand the physics and the stakes. It is also operating against a timeline that compresses quickly once a significant CME launches during the geo-effective window. The early warning time is real, but it is not generous, and there is no pause button. Part 20. The 3 possible outcomes. Every unfolding situation of this kind has a probability distribution over outcomes, and it is worth being explicit about what the 3 main branches of that distribution look like for active region 4436 over the next week. The first scenario is decay. In this scenario, the region's flare cadence drops significantly over the next 24 to 48 hours. The magnetogram evolution shows stabilization, or simplification of magnetic complexity. UV and EUV imaging shows declining activity. By the time the region enters the geo-effective window around May 13th, it is producing only C-class events, or has gone quiet entirely. Central meridian passage on May 14th or 15th is a non-event from a space weather perspective. The watch window closes without incident. This scenario is possible. It is not supported by the trend we've observed so far, but trends can reverse. Solar physics does not always follow the most dramatic available trajectory. The second scenario is sustained M-class activity. The region maintains something close to its current behavior, periodic M-class flares, CME production at intervals similar to the recent past, as it rotates through the geo-effective window. This produces several Earth-directed CMEs of the type represented by the May 10th event. The most likely geomagnetic consequence is G1 to G2 storm conditions on one or more occasions during May 13th through 16th. Minor to moderate impacts on satellite operations, radio communications, and power grid monitoring systems. Auroras visible at higher latitudes. Manageable effects on infrastructure that require attention, but not crisis response. This is the most likely scenario given current indicators. The third scenario is escalation. The region continues the upward intensity trend that went from M2.6 on May 7th to M5.7 on May 10th, a clear escalation across 3 days. In the escalation scenario, the next significant event reaches the upper M range or crosses into X-class territory. An X-class flare paired with a fast CME from near central meridian would produce significantly more severe potential impacts. If the CME carries sustained southward BZ, G3 to G4 conditions become realistic. If multiple CMEs interact in a Cannibal scenario, the upper end of the distribution extends further. Under this scenario, the infrastructure impacts discussed earlier, satellite operations, high-latitude power grids, radio communications, GPS accuracy, become more severe and more widespread. The probabilities across these 3 scenarios are not easy to characterize with precision at this distance from the critical window, with the observational data still accumulating. Forecasters will be updating their assessments daily, in some cases hourly, as the region moves towards central meridian and as the flare and magnetic evolution data accumulate. The scientific community will not commit to a single scenario because that is not how probabilistic forecasting works. What they will do is narrow the distribution as evidence accumulates, adjusting the weights on each branch as the data comes in. What we know right now is that the middle scenario, sustained M-class, moderate impact, is well supported by what we have observed. The first scenario requires a trend reversal for which there is currently no evidence. The third scenario requires the continuation of an escalation trend, for which there is currently suggestive but not conclusive evidence. None of those are comfortable categories. The middle scenario is manageable but not negligible, and the tail risk, the scenario 3 branch, is not negligible either. Part 21. The low probability, high impact scenario. Let us spend some time in the uncomfortable end of the probability distribution, because this is where the genuinely alarming possibilities live, and because probability alone should not determine how much attention we give to a scenario. A 1% chance of something catastrophic deserves more operational attention than a 50% chance of something minor when the consequences of the catastrophic outcome are sufficiently severe. The specific scenario I want to describe has 3 sequential components. It is not the most likely scenario, but it is physically plausible given what we know about active region 4436, and its consequences would extend well beyond the manageable effects of the middle scenario. The first component, active region 4436, produces multiple fast CMEs in quick succession during its central meridian passage window, roughly May 14th through 16th. The cadence we have observed, M-class events separated by 24 to 72 hours, is consistent with this. 2 CMEs launched within 24 to 36 hours of each other from near central meridian geometry would both be headed generally in Earth's direction. The second component, the faster second CME, or a third CME in sequence, overtakes the earlier plasma cloud in the interplanetary medium between Sun and Earth. The time and location of this overtaking depends on the relative speeds of the 2 CMEs and the distance from the Sun, roughly 1 astronomical unit, or about 150 million kilometers. If the catch-up happens before Earth arrival, the Cannibal structure arrives as a single, amplified magnetic structure. If it happens at or near Earth's orbit, the impact event has characteristics of both sequential and compound arrival. The third component, the merged CME structure, carries a sustained southward Bez magnetic orientation. This is the crucial amplifying factor. A fast Cannibal CME with strong sustained southward BZ is the recipe for the most extreme geomagnetic storm outcomes. The Bez drives efficient coupling between the arriving plasma and Earth's magnetosphere. The storm duration extends. The storm intensity peaks at levels that activate response thresholds across multiple infrastructure categories. In terms of effects, major G4 to G5 conditions would produce geomagnetically induced currents in long-distance power transmission lines, particularly at high latitudes. The physics here is well established. Varying geomagnetic fields induce quasi-DC currents in conductors that are oriented generally north-south, including power lines, pipelines, and communication cables. These induced currents can saturate transformer cores, causing overheating, damage, or in severe cases, permanent failure. The extreme events of 1989 and 2003 produced documented transformer damage and grid failures. Satellite drag would increase significantly across low and medium Earth orbit, requiring emergency maneuver calculations for many of the tens of thousands of objects currently tracked in those regimes. High-frequency radio communications would be substantially disrupted globally, with severe impacts on aviation and maritime navigation that rely on these frequencies over polar routes. GPS accuracy would degrade across wide areas. I want to be very clear. This specific compound scenario is not the forecast. It is not even close to the central estimate of what the next week looks like. It is the scenario that exists in the tail of the probability distribution, the outcome that is possible but not probable. It earns attention not because it is likely, but because it is physically plausible, and because the consequences of underplanning for it are substantially worse than the consequences of overplanning. The infrastructure most vulnerable to it is the infrastructure most people are least aware of. The warning time, if all 3 components materialize, could be as short as 15 to 40 minutes between Bez measurement and peak impact. That gap, between seeing the threat and experiencing the impact, is the uncomfortable truth at the center of space weather risk management. We are very good at monitoring. We are reasonably good at forecasting. We are not as prepared as we could be for the worst-case version of what a region like active region 4436 is capable of producing. The low probability, high impact scenario is not on the news tonight. It probably will not need to be, but it is physically real and it is worth knowing about. Part 22. The Current. Quiet. Revisited. We started this video at 1319 UTC on May 10th, 2026, with a violent solar eruption that should have been a major geomagnetic event and was not, because geometry prevented it. We have now spent considerable time building the case for why the next several days deserve careful attention. Let me bring you back to the present moment before we close. Right now, as you watch this, Earth is in a state of near-perfect geomagnetic quiet. The storm warning boards are clear. The K-index is sitting around 2. The solar wind at the L1 point is blowing at a steady, undisturbed 400 km per second with a weak, northward-oriented magnetic field. By the numbers, if you were a space weather operator logging conditions for a routine shift report, you would write something like quiet, no significant activity, no watches or warnings in effect. You would not be wrong to write that. Every instrument reading confirms it. It is, by every measurable standard, an ordinary day in near-Earth space. An active region 4436 is at East 65, moving toward East 52 by tomorrow, rotating toward a geometry that changes everything about what those same instruments will read within the week. Let that contrast sit for a moment, because it is doing a lot of work. The gap between these two realities, the complete quiet of today, and the potential for dramatic activity within days, is not a gap produced by secrets or suppression or dramatic narrative license. It is not a gap manufactured for the purposes of an alarming video title. It is the natural consequence of the way solar activity works. It builds, it rotates, it deploys when geometry aligns. And right now we are sitting in the space between the build-up and the alignment. We are in the calm section of the story, the part before the third act, the part that feels ordinary right up until the moment it does not. We are watching the timer run. We're tracking the degree countdown from 65 toward the central meridian. We're reading the magnetograms and the flare cadence data, and building probability estimates that update in near real time. And the instruments that are currently reporting quiet are the same instruments that will be the first to scream when the geometry changes. They are not broken. They are not being suppressed. They are accurately reporting the present. The present just happens to be the quiet before something that may not be quiet at all. The quiet is real. The concern is also real. These two things can be true simultaneously, and understanding that they can is maybe the most important thing this video offers. The absence of visible impact today is not reassurance about the next week. It is context. It is the baseline before the experiment. It is the KP2 that makes a potential KP7 feel like a discontinuity rather than a continuation. The contrast is the point. If the instruments were already elevated, if the magnetosphere were already disturbed, the arrival of another event would feel like more of the same. Instead, we're sitting at the quietest possible baseline, watching a region with a documented escalation history rotate toward the position where escalation becomes our problem specifically. Think about what active region 4436 has already shown us. It produced an M2.6 flare on May 7th from behind the solar limb, before we could even fully observe it, before a complete magnetic assessment was possible, before it had officially announced itself to the monitoring community. 3 days later, it produced an M5.7 from East 65, paired with a 650 km per second coronal mass ejection, complete with Type 2 radio burst confirmation and a 10 cm flux spike to 550 solar flux units. That is not a region introducing itself gently. That is a region that arrived already knowing what it was doing. A born complex structure carrying pre-organized magnetic energy from beneath the solar surface, skipping the developmental curve that forecasters rely on to calibrate their probability estimates. And the trajectory between May 7th and May 10th was upward, not flat, not declining, upward. The second significant event was stronger than the first. If you drew a line through those two data points and extended it forward, the line does not point toward quiet. It points toward continued or escalating activity during the exact window when the geometry shifts to maximum Earth exposure. Now, I want to be precise here, because precision matters, and this channel does not trade in false certainty. Extending a 2-point trend forward is not a forecast. It is a concern. Solar flare sequences do not always escalate linearly. Regions can stabilize, can partially deplete their energy budget, can shift into configurations that are less favorable for major events. The decay scenario is real, and it is possible. We're not here to tell you catastrophe is coming. We're here to tell you that the indicators pointing away from the decay scenario currently outnumber the indicators pointing toward it, and the window during which that balance of indicators matters most opens in approximately 4 days. 4 days is not a long time. It is not long enough to build new infrastructure. It is not long enough to redesign satellite orbital strategies. It is barely long enough for a formal operational space weather watch to run through its full cycle of issuance, confirmation, and response preparation. What 4 days is long enough for is paying attention, updating your awareness, understanding what the monitoring data is saying and what it is not saying, knowing the difference between quiet today and safe this week. That difference is the entire content of this video, and it is a difference that the headline numbers, the KP2, the clear warning boards, the undisturbed solar wind, do not communicate on their own. Space weather has a visibility problem that is almost unique among natural hazards. A hurricane announces itself days in advance with imagery that anyone can understand intuitively. A large earthquake has precursor seismicity that, while not precisely predictive, at least keeps the hazard in frame. But a solar active region rotating toward Earth-facing geometry produces no visible signal at ground level during its approach. The sky looks the same. The instruments that non-specialists have access to report quiet. The event, if it comes, arrives with perhaps 36 to 48 hours of CME travel time warning and 15 to 60 minutes of magnetic orientation warning, the two numbers that actually determine whether the impact is moderate or severe. In between the nothing is happening of today and the potential something is happening of next week, there is almost no intermediate signal that reaches most people. That gap, the gap between the solar physics data and the public awareness of what it means, is exactly what this channel exists to close, not with alarm for its own sake, not with predictions dressed up as certainties, with the actual numbers, the actual physics, the actual timeline, and the actual uncertainty bands around all of it. Active region 4436 is at East 65 today. It will be at East 52 tomorrow. The experiment begins around May 13th. The peak exposure window runs through May 16th. Those are not dramatic embellishments. They are the arithmetic of a star rotating at 13 degrees per day. The quiet is real. Enjoy it. It is what the instruments say, and the instruments are not wrong. But the region is rotating. The geometry is changing. And the baseline you're sitting in right now, this KP2, this undisturbed solar wind, this ordinary Thursday in near-Earth space, is not a promise about next week. It is a starting point. It is where the story is right now, before the next chapter begins. And the next chapter begins whether we are watching or not. The sun does not wait for an audience. We will be watching, you should be too. Because in a few days, the geometry that saved us becomes the geometry that counts. And when active region 4436 reaches central meridian and decides what it wants to do next, the quiet you're sitting in right now will feel like a very long time ago. Part 23. Final framing. In a few days, it won't miss. Let us return to where we started, May 10th, 2026, 1319 UTC. An M5.7 flare paired with a 650 km per second coronal mass ejection. Multi-signal confirmation across X-ray, radio burst and coronagraph channels. Language from monitoring communities that rarely reaches for words like extremely violent and colossal. And then, nothing. A KP of 2, an undisturbed magnetosphere. A quiet planet turning under a quiet sky. Your Tuesday, completely intact. The paradox is not a contradiction. The paradox is a geometric accident, and like all accidents, it is temporary. Let us be honest about what we actually know. Active region 4436 has shown us, in the past 3 days, exactly what it is capable of. It produced M-class flares before we could even fully observe it, before a complete magnetic assessment was possible, before forecasters had a clean look at its structure, before it had officially introduced itself to the monitoring community in any meaningful way. It escalated from M2.6 to M5.7 in 72 hours, not sideways, not down, up. It left multi-signal confirmation across every space weather instrument pointing at the sun. X-ray flux, type 2 radio burst, 10 cm flux spike, coronagraph confirmed coronal mass ejection. Every independent detection system told the same story. It behaved like a born complex region carrying energy. It did not build gradually, but arrived with, from beneath the solar surface, organized and ready, skipping the developmental timeline that forecasters depend on to calibrate their risk models. It did all of this from East 90 and then East 65, positions that sent its eruptions off into the interplanetary void, aimed away from us, felt by nobody. The plasma cloud that left the sun at 650 km per second on May 10th is still travelling right now, expanding outward through the solar system in a direction that has nothing to do with Earth. It will dissipate somewhere in the void between here and wherever it was aimed, undetected, unmeasured, irrelevant to anyone standing on this planet. We will never know what it felt like to be in its path. We were not. In approximately 4 to 5 days, none of those positions will describe where active region 4436 is. It will be at central meridian. It will be the point on the Sun facing Earth most directly. The bullseye of the solar disk as seen from our position. The geometry that maximizes the probability that whatever the region produces next will have our address on it. Every CME cone centered on its axis will have Earth somewhere within range. The 65 degrees that saved us on May 10th will have been rotated away, one daily increment at a time, replaced by 0 degrees, by the direct alignment that transforms a colossal event aimed somewhere else into a colossal event aimed here. The same energy, the same magnetic physics, the same escalating active region, different geometry, completely different outcome. And I want to take a moment here to acknowledge something, because this channel takes the honest version of events seriously, even when the honest version is less dramatic than the alarming version. What happens in that window is genuinely uncertain. The decay scenario exists. Regions do wind down. Magnetic complexity does sometimes resolve without a major release. The energy that powered May 10th's eruption may have partially depleted the stress in the field configuration, leaving a quieter, more stable structure to arrive at central meridian. That scenario is real, and we should not dismiss it. If the region goes quiet over the next 48 hours, if the magnetogram evolution shows simplification rather than continued complexity, if the flare cadence drops to C-class events or below, that is data 2, and it would shift the probability distribution meaningfully toward the benign outcome. But here is where we have to be precise about what the data we actually have says, as opposed to the data we would need to feel reassured. The escalating cadence, M2.6 to M5.7 across 3 days, is not the signature of a region entering its quiet phase. The Born complex structure, which arrived at the surface already carrying pre-organized magnetic energy, rather than building it gradually, is not the signature of a system with a shallow energy budget nearing depletion. The pre-visibility flare history, erupting from behind the limb before Earth could even fully observe it, is not the signature of a region that started strong and is winding down. Every indicator we have points toward a system that has been building, not releasing. The data we have looks more like a system approaching something than a system retreating from something. And the infrastructure exposed to that window is not the infrastructure of 1989 or 2003. It is not the infrastructure that the storm classifications were originally designed around, built in an era when satellite dependency was minimal and GPS was a military novelty rather than the invisible backbone of global logistics. It is the infrastructure of 2026, tens of thousands of active satellites in low, medium and high Earth orbit, GPS-dependent supply chains, navigation systems, precision agriculture, financial transaction timing, emergency dispatch routing, high-frequency communication networks that aviation and maritime operations depend on across polar routes, high-latitude power grids carrying more load than they were engineered for, in a world where electrification has expanded faster than grid hardening has kept pace, and a global society that has integrated space-based services into daily operations in ways that were theoretical 20 years ago and are quietly, invisibly indispensable today. This Starlink generation, the always-on, always connected, always dependent generation. A geomagnetic storm that would have been logged as significant but manageable in 2003 lands on a fundamentally different target in 2026. The same storm intensity, the same KP number, the same induced current magnitudes, different consequences, because the systems exposed to those consequences have multiplied and deepened their dependencies in the intervening 2 decades. This is not alarmism, it is infrastructure arithmetic. More dependencies means more exposure. More exposure means more consequences per unit of storm intensity. The storm classification scale has not been updated to reflect that change. The KP number you see on a forecast discussion is the same KP number that appeared in forecast discussions in 2003. What it means for the world that receives it is not the same. None of this means catastrophe is coming. Probability distributions are wide, and the middle of that distribution, the G1 to G2 baseline scenario for a direct hit from a region of this demonstrated intensity, is manageable. Satellite operators deal with G2 conditions routinely. Power grid operators have procedures for elevated geomagnetically induced current risk. Radio operators know how to route around HF disruptions. The middle of the distribution is not the end of the world. It is an operationally busy week for a set of professionals who are well trained and generally well prepared. But the manageable middle does not eliminate the tail, and the tail in this case is a physically plausible scenario, not a theoretical worst case conjured for dramatic effect, but a scenario grounded in the demonstrated behaviour of this specific region, involving a born complex, escalating active region, reaching optimal Earth-facing geometry with a documented history of violent events, potentially producing multiple CMEs in close succession, potentially generating the Cannibal CME interaction that amplifies two moderate events into one severe one, potentially carrying the sustained southward B's orientation that maximizes geomagnetic coupling. The stars did not have to align for that scenario to be worth taking seriously. The degrees just had to count down. 65 degrees today, approximately 52 tomorrow, 39 the day after, 26 and inside the geo-effective window by May 13th, central meridian by May 14th or 15th. The arithmetic is not complicated. The implications are not subtle. The sun does not have a calendar. It does not know that May 14th or 15th is the day. It does not know we are watching, that we have built networks of satellites and magnetometers and coronagraphs and solar wind monitors precisely because we learned, the hard way, on multiple occasions across the past century, that being surprised by this particular star is expensive. It does not know we have built a civilization that can be disrupted by the same magnetic physics it has been following for 4.5 billion years, long before there was anything here to disrupt, long before the first human looked up at the sun and had any idea what they were actually looking at. It just rotates, it just builds, it just releases when the physics demands release, regardless of what day it is, regardless of what infrastructure happens to be in the path, regardless of whether the KP index on the day before said quiet. We have been standing beside the highway all this time. Active region 4436 has been firing at high speed since before we could see it, and every single shot has gone somewhere other than our direction. Everyone. That is the sum total of our good fortune in this story. Not resilience, not protection, not the strength of our magnetosphere, not the readiness of our infrastructure, not any decision any human being made, just a number, 65. A coordinate on a rotating star that happened on this particular day to point the wrong way. That number is counting down, 13 degrees at a time, every single day. In a few days, it will not miss.